Hi everybody, Physics Ninja here. Today what I want to do is use conservation of energy method to solve a vertical spring problem. And here's my problem. I have a spring that has a natural length L0. I'm going to connect a mass to it of 300 grams. It's going to stretch that spring a little bit and come to an equilibrium position. I'm then going to stretch it a little bit more, all right, an extra 11 centimeters from that equilibrium position. And I'm not just going to release it. I'm going to give it some initial velocity, some initial kinetic energy to get it going. I want to find what is going to be the maximum height of this mass. Now, I'm going to show you two methods to solve this problem, okay? The first method is algebraically a little bit more complicated. The second method involves a trick, but in order for you to understand that trick, you have to understand the first method. All right, like with all my videos, if you like it, give it a thumbs up. Consider subscribing to Physics Ninja. It's the best way to support what I do. All right, let's get started. All right, I first start looking at this mass here in equilibrium. So I have the initial setup here. This is the natural length of the spring. It has a spring constant K. When you hook up the mass, it stretches that spring a little bit, some distance y0, that I'm calling 25 centimeters here in this problem. Now, when it's down here and just resting, it is in equilibrium. So if you do a free body diagram on that mass, it should look like here on the right. I have the weight of the mass acting down, and I have my spring force. Now, the spring force, if you remember, is given by Hooke's law. It's typically written as minus kx. Minus tells you something about the direction, but we already know the direction has to be pointing up. The magnitude of the force is the spring constant times the amount of stretching that you do from the equilibrium, from the natural length of the spring. So in this case, given this problem over here, it's simply K times Y0 because that's the amount of stretching that you get. Now what you do is you set up an equilibrium condition. If this block is just sitting there, it means that KY0 must be equal to the weight. So this allows me right away to solve for that spring constant K. Now, you can also switch these around and also kind of calculate that y0 if you knew the spring constant. In this case, we're going to use this left side because we know the amount of stretching that we had. So let's say we want to calculate the value for little k, that spring constant. We have our mass, which is 300 grams, 0.3 kilograms. We have little g, which is 9.8. And then we simply have to divide by the amount of stretching y0. 25 centimeters is 0.25 meters. Put that in the calculator, I think you should get 11.76, and that should be in units of newtons per meter. So that is going to be my spring constant. Let me just highlight that value. We may use that later on to calculate spring potential energy. All right, I'm going to show you first method 1 on how to solve this problem. Method 1 says this: I have to choose a 0 somewhere when I define some energies like spring potential energy and gravitational potential energy. For method 1 to work, what you have to do is we're going to set the 0 right here. Okay? Before I connect the mass, that is my 0. That means everything up here is going to be a positive value for the height, and everything down here is going to be a negative value for the y values, okay? So this is how you use method 1. So now we would simply compare what is the initial configuration, this is initial, to the final configuration. And now since there is no friction in this problem, we say that energy is conserved. So we first look at the total energy at the starting point, the initial point. Well, we're going to have some initial kinetic energy. We're going to have some spring potential energy because the spring is stretched a certain distance from this equilibrium position. And then we're also going to have some gravitational potential energy in this initial configuration. So how would I write each one of those terms? Well, this is what it would look like. The kinetic energy is always the same. It's 1/2 the mass of the block multiplied by that initial velocity squared. All right, what about the spring potential energy? That's 1/2. K is the spring constant. Now it gets multiplied by how much you stretch the spring. Okay, in this case here, I'm going to write it so it's this distance over here, from the 0 all the way to this initial configuration. So I'm going to write it as y0, that initial stretch, plus the extra amount here that I'm calling A. All right, and I have to square that value. All right, what about the gravitational potential energy? Gravitational potential energy is usually written as mg times the height. But the 0 is set right here for method 1. So that means I am below that 0. So I'm going to write it as this, minus mg multiplied by the y. How much am I stretched over here? Well, I'm stretched the exact same amount as I am for the spring. So this here should be y0 plus a. This is the total energy of the system, so it's equal to the initial and the final place. Now, if you substitute the numbers, this is what you should get. So my initial kinetic energy is 1/2. The mass is 0.3, and that initial velocity is 2 squared. You should get a value of 0.6 joules for this one. For the spring potential energy, I substitute the values, 1/2. I've already found the spring constant, 11.76. And now this number here, this is y0 plus a. y0 is 25 centimeters, a is 11. So this becomes 0.36, 36 centimeters. If you square that, I should get 0.76 joules of spring potential energy. And what about the initial gravity? Well, now I have the minus in the front because it's below that starting point. And actually, let me just go ahead and substitute the numbers in right away. So you get 0.3 for the mass, 9.8 for this, and then 0.36 for that initial total distance below that equilibrium position. I get minus 1.0, let me just say 58 joules. So you sum all those up, that means that this total energy here, at this configuration, at those numbers, you should get like 0.302 joules. All right, that's a great start to this problem. All right, now we have to look at the total energy in the final configuration. Now, one thing to remember about this final configuration is I'm at the maximum height. So that should tell you something. So let me go ahead and write down the total energy in the final configuration, or at the maximum height. Now again, if you were going to write each one, you would say K final plus 1/2 KY final squared, and then plus mg y final. I don't know if it's going to be above or below this initial starting point, so I'm just going to write it like this. Now, at the maximum height, we should realize that the speed is 0, so there is no final kinetic energy. So all we're left then is to solve this equation for y final. All right, so you could do it numerically first, because all we have then is that this energy is equal to the total energy of the system. Well, it's also equal to the initial energy, the 0.302 joules that I found over here. All right, let's just continue doing this problem algebraically. Okay, so you see we end up having to solve a quadratic equation. Now, to simplify this a little bit, I'm going to eliminate the terms in the front of y final squared. It's going to make solving the quadratic equation a little bit easier. What I do is I simply multiply both sides by 2 and then divide by the spring constant, and this is what I get. I get y final squared plus 2mg y final divided by that spring constant, okay? And I'm going to bring E total on the other side, but I get minus 2 E total I divided by that spring constant again. And this here must be equal to 0. All right, one thing that we could note here is that mg over k, and you don't have to do this, but I just kind of like to do it. Mg over k is equal to that initial amount of stretching that I have. So I'm going to simplify this. So y final squared plus 2 times y0 multiplied by y final minus 2 times E total I divided by k. Now you could do this with numbers. No one is stopping you from doing that. All right, so now you write down the quadratic equation, ayf squared plus byf plus c equals to 0. And you can see now we could solve this right away. We can write down the solutions. So y final equals to minus b, it's minus 2y0 plus or minus square root of, again, 2y0 squared minus 4. A is 1 for this problem. And now c is this whole thing. C is minus 2 E total I divided by k. And all of this gets divided by 2a, 2 times 1. Well, let's simplify some of these 2's. So again, if I divide through by 2, and I bring this 2 under the square root, it's going to eliminate all of these guys. So maybe make sure you understand that point. So that means that my final result here is minus y0 plus or minus square root of y0 squared. These minus signs, kind of combine them, turn it into a positive, and I get 2, that total energy that I calculated, I over that spring constant. All right, these are all numbers now. You can simply substitute inside your equation, and this is what I'm going to end up getting. Okay, I'm going to get y final equals 2. This is minus 0.25 plus or minus. Now, if you evaluate this square root term, again, you're substituting 25 centimeters for y0. Using this second term, I think I got for this second term 33.7 centimeters. So that means we have 2 solutions if I use the positive and negative. So let's at least write down both of those. So here's the first solution. If I use the upper sign, the positive sign, I'm going to get 0.087 meters, which is equal to 8.7 centimeters. And in the second one, what I'm going to end up doing here is I use the negative sign here down at the bottom, and I'm going to get a value of minus 0.587. This is minus 58.7 centimeters. All right, let's go have a look at the figure and see what this means. All right, so here's our figure, and I've listed some of the values here on the figure, and here were 2 solutions that I had. So why do you get 2 solutions? Number one, first of all, they are always defined with respect to the 0, right? And for method 1, the 0 is right here, okay? So the first solution actually corresponds to 8.7. Notice that it is positive 8.7. So actually the way it's drawn here is not accurate. Actually, this mass here should be somewhere up above here, and it should be 8.7 centimeters above this, okay? Centimeters. That's what it means, all right? This is where the mass is when the final velocity here is equal to 0. Now, why do you get another solution? Well, when you use conservation of energy, what the other solution means is minus 58.7. Again, that is measured from here, and minus means I'm going down, okay? Imagine I went down 58.7 centimeters. Well, that means actually, what if instead of doing this, you actually launched it down with an initial velocity of 0? Okay, the kinetic energy would be the same, and then you would get a total stretch here of 58.7. All right, so this is all it means. Okay, so you're getting this solution. This here would be the lowest solution if you fired it in the down direction, but you're not doing that. We're firing it up. So actually for us, the maximum height here has to be 8.7 centimeters. All right, this is method 2. Now, method 2 is easier. However, there is a trick to method 2, okay? And this is the trick. First of all, you set the 0 at a different position. The 0 is now set at the equilibrium position right here. That's number 1, okay? So it's a different 0 position. Different 0. Number 2, this is kind of where the trick is, and it's a little bit odd, but we don't include gravitational potential energy, okay? You don't include this term. I'm going to show you how you would apply it to this problem now. So we look at the initial configuration is still down here. That's my initial, and my final is going to be this y final again. This is how I would write the energy, okay? So at the initial configuration, again, I am setting a different 0. The 0 is right here. So all I have now is some spring potential energy because I'm stretching it, okay? And now I'm also going to have some initial kinetic energy. I do not include gravity, which is a bit weird, okay? In the final configuration, when I'm at the maximum height, I'm going to have some spring, and I may have some kinetic if I'm evaluating at some other point, but we know at the maximum height, we just set that term to 0, so that's really simple. Notice I don't have gravity anywhere. That's method 2. All right, now, the spring initial energy is 1/2 K. Now, what is the amount of stretching that you have? Again, everything now is with respect to the new 0 for method 2. So the amount of stretching that I have is only this 11 centimeters. That's the A value. So it's Ka squared. Plus, what is that initial kinetic energy? That's the same as what I had previously. 1 half mv0 squared. That doesn't change if I change the 0 position. So what is the final spring potential energy? It's 1 half ky final squared. Now again, y final is measured always relative to the new 0 position. It's not the same reference point. So all you have to do now is solve for y final. You see, this is pretty straightforward, right? The math is super easy. You can cancel out the y's. I could divide through by k. That'll get rid of this one. And it's going to introduce a k value here for the second term. And then you take the square root. So right away, I don't have to solve some complicated quadratic equation. I can right away write this number as y final equals, there's still two solutions, plus or minus, square root of a squared, and here plus mv0 squared divided by k. Now I could substitute the numbers. Y final equals plus or minus. All right, what is a squared? Well, that's 11 centimeters, 0.11 squared. The second term is 0.3 times the speed squared and divided by that spring constant, which I solved for before, 11.76. Look what we get here. We get 0.337 meters. I'll write it in centimeters here, plus or minus 33.7 centimeters. Notice what this term is. This is the exact same term that appeared in the square root in method 1. Now, what does it mean? It means that the maximum height is going to be plus or minus 33.7. So one of the solutions is up here. It means relative to this 0 point, I am going to be at 33.7 centimeters above that point. Another solution is being 33.7 centimeters below that point. However, I want to get the maximum height. So again, I'm going to just take the positive value. Forget about this guy. So this is what it is. Now we're measuring it with respect to the 0. Notice it's the exact same position because we still have y0, which is 25 centimeters. So once you find this position relative to this new reference point, you could then go back and say, well, with respect to the first reference point, right, it would simply be 8.7 centimeters above that point, right? We're still getting the same final distance. We're just measuring it with respect to a different 0. What makes this a little bit weird is that we don't include anything to do with gravity when we use method 2. Gravity gets already included when you find this equilibrium position. So that's why this method works. Now I can show you the math, and I'll do that in the next part of the video, but you can solve it here just by using method 1 or method 2. You have everything you need now. If you really want to understand why this is, you have to do it algebraically, and I'll show you that. All right, so why does method 2 actually work? It certainly is mathematically a lot simpler, but you need to look a little bit more closely at method 1. So I go back to the method 1 and my initial total energy that I had with respect to my 0 position being here. Now, what I didn't do in the first problem is I didn't kind of figure this equation out. I just substituted the numbers. But what if we did a little bit of algebra? What would it look like? What if I actually expanded these terms? So what do we get? We would get y0 squared plus a squared for the square root of each term, and then we would get the cross term, which would be 2y0 multiplied by a. Now over here, I can just multiply that through mg times y0, and then minus mg times a. Now this looks kind of messy here. However, we have to also notice that our spring constant k can be written in terms of y0. So let me go ahead and play around with these equations a little bit. There's nothing I can do with the kinetic energy term, okay? Now this k value, what I'm going to do here is, let's just multiply it through. 1 half k y0 squared plus 1 half k a squared. Now the next term becomes, see those 2's cancel out, so you get k y0 a, and then I get the two terms from the potential energy. I told you this was going to look messy, and it does. However, this is where the magic happens. Okay, now there's going to be some terms that cancel out because I have to make this substitution. Let's get rid of k here. 1 half m v0 squared plus 1 half. Now the k, I can write it as mg over y0. and I still have the y0 squared. I'll leave this second term alone because there's nothing that's going to simplify that term. And now let's look at this term. Again, for this k, I'm going to substitute. This is going to be mg over y0. I have another y0a here, and then I write down these two terms for potential energy. And now you're going to see some things that are going to start to simplify. Takes a while. So this y0 can cancel with that one. What else? I have a y0 squared here that can cancel with this one. Okay, now let's have a look at this. Here I have mg times a, and here I have minus mg times a. This term is the exact same as that one, just with a different sign. So that simplifies. You can get rid of it. The other thing you have here is you have a positive 1/2 mgy0, and here you have a minus mgy0. So what does that give us? You can combine both of those terms. So at the end, this is what you're left with, that initial kinetic energy. You get some spring potential energy that's like this, and then here you get minus 1/2. Again, this is mgy0. Okay. But have a look at this term. Okay. So the first term is kinetic energy. There's nothing you can do to simplify that. This is spring potential energy, but look at it. It's only including the amplitude, right? It doesn't include this initial stretching. Now the last term is the one that includes a little bit of that stretching here. However, think about what this term is. This term here is a constant value, okay? So if you have it here in the initial configuration, you're also going to have it in the final configuration, right? So right away, I could write down the final energy of my system here as being final kinetic energy plus 1/2 ky final squared. And then I'm still going to have a constant value, minus 1/2 gy0, okay? At the end, again, this is measured with respect to that equilibrium position. So this here also gets measured with respect to that equilibrium position, okay? And the constant terms are going to be on both sides of the equation. Sorry, there should be a mass over here. Since the constant term is not going to contribute anything because it's going to be on both sides of the equation. And that's why you see method 1 actually simplifies to method 2, right? This is basically method 2. We've just redefined the zero in the problem. All right, anyway, this is kind of the background behind it. Hopefully you appreciate this and you are able to solve problems using either method.